Hey everyone.
Okay, how you doing, John? All right, let's everyone mute, and I'm going to start the recording, and we'll get started. How's that sound? Okay, I'll record the meeting. All right, I'm going to get started. It is a major pleasure for us to welcome Benjamin Cabé here today. He's a software engineer and a researcher from Microsoft, where he specializes in IoT and integration into cloud services. Before working at Microsoft, he has worked at Eclipse Foundation. In fact, he's got a dedication to open source projects dating back for over a decade, which tells you a lot about where his heart is. And so he was immediately a cool guy for us to chat with. I first met Ben on Reddit, where he posted his project. And he didn't use a lot of words. He just posted a small video of his project and says, smells like TinyML in here. And when I saw that, I immediately reached out, because there's two things that were cool about that. One is that instead of just talking about it a lot, he just showed what he did, and you can see it in the video, like a very short video, exactly what that project was doing, and it summarized it all. He doesn't do a lot of discussion around that. And when I reached out to him, the other thing I found out is that he wanted to understand how AI works. You can do as much as you want by loading in data sets and then making it show that you can, classify things, but he felt that he didn't understand AI until he actually did it himself. And so that's exactly what we're trying to do with our summer fellowship program here. And so it's kind of also a mix of AI and neuroscience, right? And it's a tractable project for kids. And so you can see why we got very excited that Benjamin was able to join us today. And apparently I was not alone at noticing that. If you pick up the current issue of Make Magazine, you'll see his face on the cover with his device. So that's kind of cool. If you're not familiar, Make Magazine is the #1 maker journal in the world. So it's like anyone who does, they're not just cool projects, they're like super cool projects. To make the front cover of a quarterly issue is pretty amazing. So I'm excited to talk with Ben today. We have asked him to give a kind of an overview of his project and kind of some lessons learned through that, because I think we're all struggling as we're trying to collect our data and try to get out the noise. How do we train the neural networks? And so I think it's a very big treat for us to have Ben here today. So please join me in welcoming Benjamin Cabé. Cheers.
Woo! Okay, that was quite an intro. Thanks for that. Yeah, looking forward to telling you all a bit more about this project, the story, a bit of what Greg mentioned about the fact that it kind of went viral, although it might not be super technical. Like the project itself, I don't feel it's necessarily like super deep, super bleeding edge tech stuff. The talk today won't probably be super technical, but that might actually be the point of the whole thing and the whole lecture for today. Yeah, just to add a bit maybe to what Greg said in terms of oops, is slow or scheme slides. Well, I guess I'm starting with the demo. I forgot. I thought I was starting with my quick intro. Yeah, a quick demo. Like, what is the project? For those of you, I think most of you, most of you students, might have seen the project one way or the other when you applied for the scholarship. But it ended up in the form of a 3D printed nose that uses TinyML or AI. Like, if you're not familiar with what TinyML is, you will learn a bit during the talk. Let's just call it AI for now. And yeah, the device has been trained to recognize smells when it does kind of like a wandering face. It's when it's not sure about what it is smelling, and when it's smiling and giving you a measurement, a reading, then it's when it's pretty confident that it's smelling whiskey, or when it's smelling coffee. So yeah, I will tell you a bit more about the project, like from a technical perspective. technical, meaning the AI bits, but there's also some interesting hardware story to it. And there's also the IoT. And I'm not sure, actually, Greg, you said IoT. IoT as an acronym might or might not resonate with you all. So it's the Internet of Things, this idea of having devices, and it's not only smart home devices, right? Not only home automation gadgets. It can be literally anything. Devices that are connected to the internet, right? And once you start connecting devices to the internet, you can do some cool things and sort of enable interesting scenarios, and we will talk about that as well. Now for the intro, but not a lot to say here. I've been with Microsoft for a couple of years. I'm part of the product group, the product team that works on the Azure Internet of Things platform. But my day job is not necessarily working on the new cool feature that will be added to the IoT platform. It's more about making sure that whatever we have already as part of the Azure IoT portfolio, if you will, is something that developers out there and potential users, potential customers, I guess, are aware of. And usually my approach to it is by creating demos, tutorials, all sorts of projects that can help showcase what is IoT in the first place, what are some of the scenarios, and what is some of the cool tech out there that can help you build end-to-end IoT solutions. And some of that cool tech might come from Microsoft. Some might be third-party, like open source technology. And you can find me on Twitter as well. If you didn't figure by now, I'm French, and I do like bread. I like baking my own bread. I won't tell you how old I am, but I think I've been trying to perfect my bread recipe for the past 20 years or so. And last year, just like many other folks, like it was literally a year ago, like in May last year, lots of time on my hands. I was like, hey, let's try and improve my bread recipe, and specifically sourdough bread, right? So that involves sourdough starter. Well, that involves flour as well, which, by the way, back then wasn't necessarily super easily available on the shelves. And this is kind of important for the rest of the story. But I wanted to perfect my bread recipe, and like I'm telling you, like I've been trying to perfect my bread recipe for the past 20 years, and like I'm not quite sure. Like I'm not happy about how the kind of bread that I'm getting. And I don't know. Like maybe a quick question for you all actually. What do you think makes good bread? And I don't know what's the best way for you to like give me a sense of what you think. Maybe feel free to drop in the chat or just to say by voice. But what is like Tim? What's good bread? Or what makes good bread?
The yeast you have makes it good. That's what I've heard.
Mm-hmm. Mm-hmm. Probably. Yep.
How much it ferments?
The what? Sorry.
How much it ferments?
Mm-hmm. Mm-hmm. Yep. And the answer is like, so I'm not like a professional baker, and I've been still trying to perfect my bread recipe for the past 20 years. And the answer is, I don't know. It's probably a bit of everything, right? It's a bit of what you guys mentioned. It has to do a bit with the humidity in the air, with how long you bake the bread, with how good you are at, like when you actually put it in the oven, how fast you are, so that you make sure that the temperature in the oven doesn't drop too much. It's probably a bit of everything. So my thought, having plenty of time on my hands, was let's try and maybe build a device that helps me identify sort of a subset of the potential parameters that contribute to the quality of the bread, specifically the ferments, like you guys mentioned, the sourdough. How much does the sourdough have an impact on the quality of the bread? And potentially build a device that I would use and train to smell the sourdough starter, and then I would bake my bread, and then I would that would be my data set. This sourdough, like this sort of olfactory footprint of the sourdough, this gave a bread that I would say is a 9 out of 10, right? This one, etc., right? And trying to do this training. And this is where I was thinking, this is probably my perfect excuse for me to learn AI. And like I think Greg mentioned in the intro, I'm a software engineer. Like I touch a bit of everything, like a bit of every programming language out there, a bit of every framework because that's what I do. But AI, for the past decade or so, is something that was just going above my head. Like there would be those super simple, almost hello world kind of samples that are, hey, let's classify some bitmaps with single digits, like handwritten digits written on them, and let's classify that and see it's a super simple neural network. And just like quickly, I would read a couple pages of the book or like a couple paragraphs of whatever tutorial, and I just like something was missing. So I was like, maybe this particular example being more tangible, maybe this is my excuse, right, to learn more about AI. But at least as of a year ago, I can tell you that I knew almost nothing about AI and neural networks, because simply I just couldn't understand what it was about in the first place. And so when doing some research, like I was made aware of some devices out there, open source devices from, I think this is from a lady that at least back then was working at Twilio. So Twilio, you might or might not be familiar with them, but they do APIs for sending SMSs and that kind of stuff. So I guess she has a similar job to mine, and she built a device that's not AI powered. It's dumb, I would say, sensors that simply monitor the humidity and the rise of the sourdough starter using a ultrasonic sensor, a sonar. And then whenever the sourdough is high enough and has the right amount of humidity, then it sends you a text to tell you, hey, it might be the best time to bake the bread. But I wanted to do more. And that's when I started to be like, okay, it's probably again the perfect excuse for me to start and learn AI, and more specifically TinyML, right? TinyML being this ability to take a neural network and things that you typically expect to run on super beefy machines and GPUs and whatnot, but actually like use some techniques like embedded software wise and like even like at the silicon level, using some techniques so that you can actually run inference and like do some AI on very, very small devices. And maybe more importantly, by not using a lot of energy, which might make sense, because like when you're thinking embedded device, you're usually thinking battery powered, right? And devices that are wireless and that need to work out of batteries. So like I felt back in May last year that I had an interesting idea, or at least it was tangible enough that I felt I would be solving an actual problem that I had, rather than just classifying single digits for the sake of classifying single digits. And and I had also some hardware, and we will talk about that in a minute. And all in all, like I knew at least enough about AI and machine learning and deep learning to know that my problem and my problem that was eventually going to be something that I would solve with TinyML was no different than like a typical deep learning application, right? I would need a data set, like I mentioned, training the model against some like the smell of the sourdough starter, and as a result, the quality of the bread. I would need some hardware, not in the sense of GPUs, but more in the sense of like sensors for smelling my sourdough starter. I would need to build a model, and I would need a framework. So the data set, we'll see why I'm using sort of the wandering phase there. It might not be like training a data set, building a data set where I have enough data and where I've baked enough baguettes and loaves of bread to have enough inputs might be a challenge, especially given the flour situation back in May last year, right? So the data set, we will come back to it in just a minute. The hardware, turns out that I had actually some really cool hardware at hand, and I'll talk about that. But essentially, Arduino kind of device, some very simple off-the-shelf gas sensor. I was pretty confident that was enough. Like, I knew enough about TinyML to know that it would probably be enough. The model, I was literally scared. Like, I had no idea how I could take, say, I don't know, 3 seconds of sensor data and turn that into meaningful info where potentially I would extract whatever is needed to make a deduction with regards to what makes the sourdough starter good or not, right? And I was really confused there. Framework-wise, I kind of knew that TensorFlow Lite would probably be the way to go. But again, all the samples out there, the tutorials, they're telling you how you can do very simple, maybe motion detection, but it was not necessarily enough for me to understand how I could take an existing example and adapt it to my use case. So let's see. Let's talk about the data set maybe first. I quickly realized that yes, it would probably be nice if I could build an AI and train an AI to correlate the quality of the sourdough with the quality of the bread that you can get out of it. But there was no way I was going to bake dozens and dozens of baguette. So I ended up realizing that probably I could just train a model for smelling anything, right? I have some input data, some gas sensor, some kind of gas sensor data, and as an output would be labeled smells, right? Whiskey, coffee, etc., etc. And then another challenge was, if I'm going to train a model, then I have my Arduino, my embedded kind of device where it's pretty easy to write some piece of embedded software that extracts data from the sensors, and I can get data at 10 hertz, 100 hertz, whatever. But that data, getting it from the embedded device to the environment in which I'm going to build and train my neural network might be a challenge. I don't want to use an SD card on my device to first read all the data and then take the SD card off of the embedded device and load that on my laptop or things like that. I would like something more straightforward. And for that, there is a great tool that's been available essentially pretty much when I started my project, and it's called Edge Impulse. I think some of you have been using it in your projects. It's it's an online, a browser-based tool that helps with everything that involves TinyML, all the way from acquiring your data. And here the trick, and the smart trick, is that you can essentially use your desktop computer or your laptop as a bridge between the embedded device that's going to be eventually the thing that's going to run your AI model, and it's essentially you can channel and funnel the sensor data coming from your embedded device to the Edge Impulse cloud platform through your laptop. And so with just a few clicks, you can start acquiring tons and tons of data. And then comes what I called earlier sort of the scary part, which is building a model. But with the Edge Impulse online environment, you're guided based on your data to build at least a V1, a first version of your model that will probably work well enough based on the type of data that you're manipulating. If your data is more sort of audio data, then the tool will guide you to build a particular kind of neural network. If your data is more like my data for the nose is doesn't have any sort of time characteristic to it, then it will guide you towards like a different kind of architecture. And similarly, if you have images, videos, etc., and then like in literally a few clicks, you build a model. You can train the model based on the data that you've acquired. And at the end of the day, once you have the model and you're happy with the model, you end up with some code, some embedded code that you can deploy back to your embedded device, and that's it really. And all in all, like in literally a few hours, I actually had a model trained, right? But for training the model, first I need some data, right, and some sensor data. And for that, some of you might not have been there when we were chatting earlier before the talk started. But we were talking about Seed Studio. They promoted today's lecture earlier today on Twitter. Seed Studio is a company that does open hardware equipment, just like might be familiar with Adafruit or SparkFan. They do the same, right? And they have this device which they actually released last year, and so it's no accident that I ended up using that one, because Seed Studio, they were interested in having some good demos and good content being built around their device. So just a few weeks before I started my project, they had sent me a sample of this particular piece of hardware, which is essentially an Arduino kind of microcontroller on steroids, right? It's a Cortex-M4 MCU, and just a bit more on the MCU itself in the next slide. But it's a sort of like a basic off-the-shelf MCU, which if you buy alone, you can get for just a few dollars. But around it, there is a nice enclosure. There is a way to plug in a battery potentially. There is an LCD display, buttons, etc. And then there is also something that Seed promotes quite heavily, this notion of the groove sensors, which means that like they essentially build hundreds and hundreds of sensors, and it's almost plug and play, right? You can take whatever sensor Seed manufactures and use it with the device, the Weir terminal, by the way. I'm not sure I said how it's called. And so the sensor I used is very simple, off the shelf, not super expensive scientific kind of equipment. Quite the opposite, actually. It's a 4-in-1 gas sensor that effectively has 4 sensors, and it can sense and measure the amount of carbon monoxide, nitrogen dioxide, VOCs, volatile organic compounds, as well as alcohol in the air. And it's really cheap, like it's like $30 or something, and it's really cheap, as in, like, if you look at the data sheet, the manufacturer is pretty clear about the fact that it will give you some kind of ppm readings, but don't take them for granted. It's like the sensor is not necessarily calibrated, but at least from one day to the other, a particular sensor will always give you reproducible results. And like, I felt that was enough, right, for me to get started. And we'll talk a bit about sort of the limitations of using low-cost sensors and what you need to have in mind when like on the long run, I guess. But for prototyping, it's super convenient. And I said I would say just a few more words about the brains, I guess, of the nose. And so yes, it's a Cortex-M4 from Microchip. It's fairly constrained, right? I mean, some of you might not be that familiar with embedded software development, but 200 kilobytes of RAM, 0.5 megabyte of flash. It's not a lot, but it's actually still plenty for a use case like building an artificial nose, or at least building it the way I did. If you want to classify just a handful of smells, you have plenty of memory and plenty of processing power with this particular device. And how much does that cost, by the way? I think that's something interesting to have in mind. If you're interested, like, really in the prototyping and looking at the Wii terminal as a sort of a bundled device that won't require you to do any soldering or anything like that, then you're looking at about $30. I think it's closer to 40 these days due to the sort of the silicon shortage situation, but it's still like reasonably affordable. But what's important to have in mind is, if one way or the other, this was only a prototype that you built initially, and you're looking at mass producing your device, then out of all the things that make the Wii terminal, it's likely that the microcontroller, the MCU, is the most important one and the one that you're going to need. And that one is reasonably cheap. It's $5 when you order quite a few thousand units. And again, for particular scenario of smelling a handful of smells, it might even be too powerful. So you may want to look at like a slightly different flavor of this particular MCU with half the amount of flash, half the amount of RAM, and you probably cut the price in half. So that's I think that's interesting to have in mind. So how does a machine smell anyways? How did I effectively build a model to give the nose some kind of a sense of smell? So it starts with the gas sensor, right? And so there's different technologies there for doing for measuring gas with electronic sensors, but one of the most popular and one that actually makes sensors that are reasonably affordable and really small is using a piece of metal oxide semiconductor. So it's sort of embedded within the enclosure of the gas sensor, and this piece of metal, when heated, reacts with chemical compounds in the air, and based on like the kind of sensor, it might be reacting with ammonia, reacting with carbon monoxide, etc., etc. And it's an oxidation reduction kind of reaction, which means that the resistance of the piece of metal will actually change, right? And if it's an oxidation or a reduction, the resistance will increase or decrease. But that's something that you can measure using a microcontroller is able to do that, right? And you can turn this change in resistance in a voltage. And should you have, 10 ppms of VOCs in the air, maybe the sensor will give you a reading of 100 ohms, right? And if you have way more, a much higher concentration of organic compounds in the air, then the resistance will change, right? And this is how, like with those 4 sensors that are part of this 4-in-1 sensor that I used, that's how I ended up like acquiring data and starting to use my intuition. And I was glad that for once, as opposed to those single digits thingies and like image-based recognition kind of algorithm, for this particular scenario, the things that I was manipulating were more tangible, and I could start thinking, what does really matter when it comes to a smell? And I started experimenting, and what I'm going to explain just now is essentially, it hasn't changed since my first experiment. I was like literally thinking, I probably need to acquire just a few seconds of data, just enough to capture not only on average how strong, for such or such ingredient or for such or such smell, how strong is the level of alcohol in the air, the level of carbon monoxide, etc. But that's probably not enough. I should try and capture things that are more how volatile is a particular compound, right? Like my intuition was, again, for say vodka, not only the amount of alcohol is probably through the roof when I put the sensor right on top of the bottle of vodka, but my guess is that vodka has like a really strong and steady amount of alcohol, as opposed to maybe a glass of wine, which will have some amount of alcohol in it as well, but it will likely fluctuate a bit more, because my guess is that the molecule of alcohol, they compete a bit more with the air, and they might be more volatile, more discrete, and same for VOC, etc. But so I started by acquiring like what we're looking at here. This is real data. So this is 1.5 seconds of gas sensor data acquired at 10 hertz. So that makes for 15 samples. And there seems to be already some info in there. Like it looks like some like I was saying before, like maybe the amount of VOC, it looks like it's growing fairly steadily, as opposed to carbon monoxide, which might be fluctuating a bit more. But whatever, like let's just start labeling the data, and this is whiskey, right? And that comes the next part, sort of intuition-wise, which is I'm not going to go very far with those raw samples, right? I have 15 samples for ethyl alcohol, 15 for VOCs, and blah blah blah. That's 60 samples in total. My intuition was those numbers, like I can't really fit them directly in a neural network, right? I need to sort of process the data and extract some meaningful information. Thanks to Edge Impulse, and mainly thanks to the Edge Impulse, actually, like I was guided towards cleaning up and organizing my data a bit, making sure that it's not only 60 samples, like in a bunch of samples. It's more, it's flattened, and we sort of retrieve the structure where it's actually 15 times 4 readings. Then I was just like listening to what Edge Impulse was suggesting me to do, but making sure that the numbers would be numbers between 0 and 1 to help a bit with the training phase. Whatever, so be it. Then actually running the important piece, which like I was super happy to realize that it was very much aligned with my intuition, which is running some kind of like super simple signal processing, I guess, where I would look at for each gas, the average, the minimum, the maximum, the root mean square, and the standard deviation, trying to capture the things I mentioned before, right? Like how strong, like using the average, trying to figure out how strong is the amount of ethyl alcohol, but using the mean and the max, then maybe realizing that it's strong, but it's fluctuating a bit, or it's I'm just putting the sensor. I'm just about to put the sensor on top of the glass of whiskey. How steep is the slope, right? How fast is the amount of alcohol going to grow? This is something that's captured in there, right? With all those features, essentially, that are being extracted from the raw signal.
So Benjamin, let me ask you, how did you land on these 5 features? I mean, were you experimenting with a wide range of them, or did you put
not
all
really?
of them in?
It turns out that, and this is where it almost looks like magic. But in the Edge Impulse studio, they have wizards which you go through for creating your model, and they actually suggest that if you have data that's sort of flat, you start by extracting the average, the RMS, and the min and the max, and it might already be enough. And they have a few more, but yeah, I realized it was enough, quite frankly. So yeah.
So this is just this is the flattened. So the flattened gives you these 5 things. Is that what you're saying?
Yes.
I got
five features for each gas, and then once you have that, and this is where I was like, okay, now I realize what a neural network is. I have my raw data. I take it through what I call the signal processing block. So I turn my 60 samples into effectively 20 thingies, right? The sort of the statistical characteristics of the data. And those 20 things are what you see as the input of my neural network. And then the output is the different smells, right? You have whiskey, you have coffee, and you have ambient air in in I guess the current version of the model and the one that you will find on GitHub, and I will post the link on the GitHub repo later. But that's the model, and now I could finally understand what a fully connected neural network and fully connected layers mean. It's essentially you have whatever input, whatever output, and you want just to sort of solve the equation of establishing the relationship between the input and the output. How much does the minimum amount of alcohol over a period of 1.5 seconds contribute to telling you it is whiskey, etc., etc. And like it literally clicked in my brain. I was like, okay, I almost felt like I could build this kind of neural network like in an analog way, right? With knobs and like, I don't know, wires or sand flowing through. If you were to sort of turn this diagram 90 degrees clockwise, I almost felt like it would be, I don't know, like buckets where with sand flowing, and based on how you train the model, maybe like in a particular configuration, most of the grains of sand, they would end up in the whiskey bucket because that's how you've trained the model, right? Actually, I think, there's, so I hope I didn't lose questions and miss questions in the chat, but at least now there's one from Tim. Yes.
Yeah, it's very interesting. Thank you for the time. Some of the fellows are dealing with classification right now. So you have your 20 kind of numbers that you're putting in. And how many smells is in your library? So I know you had whiskey, coffee,
yes,
wine. So
usually, so that's a really good question. So as an input, the 20 characteristics, I found out they are enough. As it comes when it comes to the hidden layers, like if you only have 3 smells as an output, then it's fine to only have, what do we have here? Like 8 neurons for the first layer and 4 for the other one. The second one, if you have 10 smells, then you might need to add just a bit more in the middle, but it's usually pretty like simple to do some trial and error, or to just follow best practices. Like it's like a super simple architecture. So I think there are some like the rule of thumb is that the first hidden layer should be half the amount of neuron that you have as an input, and then same for the second hidden layer. And usually like that works reasonably well. We'll actually talk a bit, and I realize that I'm talking way too much, so I'll probably speed up a bit. But what happens when it's tiny ML, right? You're aiming for very small and constrained devices. So the model sometimes might tell you things and give answers and results that are way off. So how do you detect that? And yes, Greg, you have a quick question, or you have a question, maybe not a quick one.
Yeah, no, it's a quick one. And first of all, you're not talking too much. I think this is we're making it a little bit more interactive here. And everything you're doing is fascinating, because I think the fellows that are here are all this is a little bit too real for us right now. The struggle is real, right? How did you come up with 1.5 seconds? Like where did this how did you come up with that? Did you do a series of experiments to figure that was a good number, or it seemed like when you're smelling it takes you that long? How did you do that?
That's a good question. I think I don't think it's a strong requirement, but my idea was to ideally build a like you maybe remember from the video at the very beginning. I wanted to do something that works in real time, as opposed to something where I press a button, the nose smells for X amounts of seconds, and then gives you a result. So it like effectively the window of data that I acquire, it's always floating, right? You guys see what I mean? Like I constantly feed data into the DSP, and so when you switch from whiskey to coffee, like there will be a short time window, say maybe a second, when the data, the data that you have in your 1.5 second slice is going to be almost garbage, right? Like it's kind of in between. And so if that window is too large, then say it's 10 seconds, then it's going to be really hard to train a model, because you're going to train the model for whiskey, you're going to train the model for coffee, but then you will have, like, sometimes you will be feeding the model with stuff that's 5 seconds of whiskey, 5 seconds of coffee, and then what, right? So for having like this kind of real-time scenario, then you don't want to have too much, and you don't want to have too little to make sure that you still capture what makes a smell character and what characterizes a smell. Now, for this issue of potentially having too large of a window and having data that's garbage, and that you will still feed in the neural network, there's actually a solution to that, which is something that also the Edge Impulse Studio guides you in potentially implementing, which is having prior to even running your inference, doing anomaly detection and using very simple clustering algorithm to, like, once you're done with all your training, you try and capture the fingerprint almost of what is your training data, so that you know, like at a general level, how did the data look like? Oh yeah, the amount of alcohol, this was usually like in this realm. This the amount of VOC, this was always like that. And so that when you're just about to run your AI, you first feed your 1.5 or 10 seconds of data into the anomaly detection algorithm to get an answer to the question: is this new fresh data that I'm going to feed you, does it look like it's similar to what we've seen during the training time? Because if it's not, it's very unlikely that the result that the model will give me or give you is going to be accurate. Because yes, it's going to give a result, because it's just a function, like a mathematical function. It's going to give an answer, but it's going to be garbage, right? So yeah, that was my long answer. But back to the real-time aspect of it, like, there's no reason why I want to do continuous inference, but it might actually be better if I were to just like have a button and make sure that whenever I capture a smell, it's like 100% that smell. But then it wouldn't work in a continuous fashion, and it wouldn't. And you would introduce a latency, right? Because you press the button and then you need to wait 1.5 or 3 or 10 seconds to get your result. So, all right. What else? Yeah. So once the model was built and trained, everything else was easy almost. In terms of framework, out of Edge Impulse, but out of anything really. Like, if you're already familiar with TensorFlow, it's pretty easy to obtain a model that is targeting TensorFlow Lite for microcontrollers specifically. And here the idea is that you have a framework that's meant to run, that's implemented in C and meant to run on very small and constrained silicon. So it's optimized for latency. It's only you're not talking about like internet scenarios. It's not like the model is in the cloud and then the device makes a call to the cloud. No, everything is meant to run locally. Everything is meant to be super efficient in terms of power consumption. Potentially, just like TensorFlow proper would use GPUs and acceleration when available, TensorFlow Lite for microcontrollers can do the same. Like as part of the ARM MCUs, there are some actual algorithms baked into the silicon that can help with not only run some operations on your neural network faster, but also save in terms of size, right? Because rather than having to compile C code, like your source code or like TensorFlow source code into code loaded in the microcontroller, this can be like the like TensorFlow can directly ask the hardware to perform the operations for it, right? And something that's also very convenient, very powerful when you prototype is that the code you get, TensorFlow Lite is something that you can run super easily on virtually any flavor of Arduino boards out there. So that's pretty interesting. A few words about performance and code size. Just like I sort of shown the kind of the minimal neural network that can get you to classify, say, 3 smells. Well, that particular network, just so that you know how small it can get, it can actually fit, and you can run an inference by just using about 4 kilobytes of RAM, just about 27 or 30 kilobytes of ROM. So that's the code size of like the model itself. So all the parameters of the neural network, they fit in about 3 kilobytes, and then the rest would be for the TensorFlow framework itself. And then something that's actually super interesting in there as a number is this particular model. If you aim for a very, very small, a small, and not necessarily very small, a small MCU, 80 megahertz MCU, you can run the inference time in under a millisecond. So 2 things here. The Wheel terminal that I'm using, I think it has like 3 or 4 times like the processing power than what we're looking at here. And second, if you remember, I'm sampling the data, the sensor data, at 10 hertz. So it means that I have plenty of time to do nothing potentially, or to do something else, right? Like I acquire data every 100 milliseconds, and then I run the data through the TensorFlow Lite model, and I get my results. And the rest of the time, which is literally 99% of the rest of the time, I can either do some graphical user interface management, or I can just sleep, right? I can have a nose that just goes back to sleep. So that's that's interesting, right? To see that it's really fast. And of course it is, because if you look at it, the network is not that complicated. There's there's probably, I don't know, a few tens of thousands of operations to run, but it's not terrible, right? And if I were to be interested in classifying more smells, my model size might grow, in which case I might want to look at quantization and having all the parameters of my model being stored as integers rather than float numbers, and that might help save quite a lot in terms of the model size. Another technique which is available through the Edge Impulse environment, and also like there are like literally tons of solutions out there to do things similar, rather than TensorFlow Lite, just like TensorFlow, is a framework, right? You have a model that is more or less interpreted at runtime by your microcontroller. How about, rather than loading a model in memory and turning that into code on the fly, how about you directly compile native code? And so that's something that can be done through the Edge Impulse Studio, and in which case you have way smaller code size, way smaller RAM footprint, but also it's faster, right? Because you're directly leveraging the silicon. And there's others techniques for accelerating. Friendly reminder of something that I just mentioned before, so I won't be long on that one. But classification, at least to the best of my knowledge, and remember, I'm just an AI imposter, so I might be wrong there, but the way I see it is, it's sort of a function, right? Like once you've trained and solved the equation based on your training data set, you have a function which you call with your fresh data, and it will give you an output. And if the data is just completely random, it doesn't matter. It will still try and give you an output. You smell strawberry jam? Sure, smells like whiskey. Or honey? Yeah, sure, smells like coffee. So the anomaly detection thingy that I mentioned before, I think it's important. And it's also important, I don't want to put too much into that, but you might remember the UI from the very beginning with the smiley face that says, not sure it's whiskey, and then the smiley face that say, yes, it's whiskey. This kind of feedback, this kind of user experience, user interface, I think it's kind of important, especially when you're looking at TinyML and that AI models that might not necessarily be super accurate and that have limitations. Ideally, those limitations you're aware of, just like I am. Like, I know that I'm using a crappy sensor. I know that my model probably didn't capture enough, either because the time window is too small, either because the neural network architecture is wrong. But at least I know some of the limitation, and surfacing that to the user, I wouldn't call that necessarily like ethical AI, but almost, right? I mean, it's important to set expectations, I think. And happy to chat more about that. But yeah, working on the user interface is important. And at this point, you're like, oh wow, that was cool, that's fun. But like Benjamin's been tinkering, right? He doesn't know anything about AI. He's using crappy sensor. Yes, that's true. That's kind of what I've been doing. But it's what's interesting is that folks like very early on, when I just like Greg described, when I started to tweet about it and so on, folks just like got really excited. So I ended up spending some time doing the full Monty, I guess, and going all the way to learning Blender. Like, I don't know if you know Blender, but I didn't, or at least I hadn't used it before. But I ended up designing an enclosure for the device, and the enclosure is now something that's effectively open hardware. You can go on Thingiverse and you can print it, and you can like get yourself the fancy enclosure. You what else? Yeah, I tweeted about the project. And this one tweet actually was already a year into the project, where I had realized that for almost a year I had dropped the ball. I never went past designing the 3D enclosure. I never blogged about it like I wanted to. I never published the source code like I wanted to. So this kind of GIF, and that's the one I think Greg found on Reddit. That was kind of a second excuse for me to sort of get motivated to potentially do more. And this one really got viral. It was retweeted and shared by an influencer on LinkedIn. And just like, I want to be pretty clear about the fact that it's like, if I might not be an imposter, but I think you realize by now that there's no super fancy bleeding edge AI in it, right? It's like the neural network that you've seen, it couldn't be more basic than that. And the use case, it's kind of cool, but it's not like I'm using thousands of sensors and solving world hunger or whatever. And yet, folks got like really super excited about it. Getting 200,000 plus views on LinkedIn is crazy, right? And that's how like eventually I got approached to write an article, and if you get to read the article, it's very similar to the talk I gave today. It's sort of telling that story of, I had an interesting or maybe not so interesting problem that I wanted to solve, and what were the different steps, right? And what are the limitations also of the design? It ended up being it recently was first featured on Mashable as well. So that's cool, I guess. But then, and this will be just as a conclusion, I'm also an IoT person. Like typically when I play with gadgets, is either it's because I'm paid to do that, or because I think it makes a lot of sense, and usually both. I want to connect things to the internet. And what happens if you have, you can probably imagine that there are some interesting scenarios if you have a device that can sort of smell when it smells nasty or funny, and then you want to deploy that particular device in the ceiling of restrooms in an office building, so that whenever it does smell nasty, you send someone to do the cleaning, right? As opposed to having the more naive approach, which is, hey, let's go and do cleaning every other day. But then what happens if for some reason it's COVID times and everything is super slow, and you don't really need to go there every other day. You could go there every week, and that would work just fine, right? So how do you do that? And how do you like solve this particular problem when the sensor is effectively stuck in the roof and in the ceiling of the room. It's not like you're going to send a technician look at the LCD display and see if it shows like the smiley face and the poopy smiley. That would defeat the purpose, right? You want this thing to be like tetherless and to be able to connect to the internet, and that's where IoT enters the room. And I mean, some would actually say AIoT, right? Having intelligent devices and connecting them to the internet. And if we are to simplify, I can leverage the fact that the Weir terminal is Wi-Fi capable, and then I can connect it to the cloud and do things like sending telemetry. And by telemetry, I mean things like maybe the raw sensor readings, or more likely the inference results. It smells nasty with like, there's a 90% chance that it smells nasty. Or sending the raw sensor data is also something that's interesting if you can do it completely like remotely, because you can acquire tons and tons of data in the cloud from your thousands of devices in the field. And this is data that might prove valuable for training or improving over time the quality of your model, right? Because you collect data that's even more representative of what can be seen in the field. And it works both ways. What's interesting is from the cloud, although your device is like completely remote and using either Wi-Fi or cellular, you can send quote unquote commands. And usually commands would be things like, hey, dear nose stuck in the middle of nowhere in the ceiling of whatever building in the headquarters of Backyard Brains, here's your new model. From now on, you can smell new things, right? Because we've deployed and built a V2 of the model. Whatever model Benjamin's built initially was just too limited, but that's fine. That was enough to start. We could still start going production with the first version, but later on, due to the IoT communication channel in place, there's no reason why the device couldn't become smarter over time, right? And so effectively, if you go and check out the GitHub project, you can actually connect it to the Azure IoT platform. And here we're looking at the device sending data in real time, which can have tons of applications, right? Either the raw sensor data or the results of the TinyML inference, or things like a technician might want to look at, or are things like that you might want a mobile phone, a mobile application to tap into using APIs. Or going a step further, and with that I will be finished. One step further would be what happens when you're like, there's tons of industries and businesses out there that already have an IT infrastructure, right, and an information system. If I'm in building management, it's very likely that I have a model, if you will, or a database of what are the cities I have buildings in? What are those buildings? What are the floors? What are the different HVAC systems? When's the last time I did the maintenance on the HVAC? Who's responsible for the maintenance and the cleaning of such and such building? And once you have that, you can start adding this notion of digital twins, which is, should you have physical devices deployed in the field, deployed in the buildings, they too can join and be part of that graph, right? And here on the bottom right hand side, you see that the nose, like at a given point in time, it's attached to a specific floor, the floor where it's deployed, right? And what happens when the IoT platform detects that nose XYZ is like sending a signal that something's wrong, then you can start navigating the graph to be like, oh, let's see, the nose right now it's in this building. Who's responsible? Oh, today is John. Let's send a text to John to make sure that they go and do some cleaning, right? And that's like beyond the buzzword, I guess. That's what digital twins allow you to do, right? You can implement those kind of scenarios and have something that's super versatile, right? You can have existing IT systems, existing databases, but then you can also tap into the physical world by having those digital twins attached to your existing entities. And with that, some links, the GitHub repo, cardben/artificial nose, everything is there. Feel free to open issues, pull requests, random questions, improve the docs if you feel like anything is missing. And hey, almost the top of the hour. Well, it is top of the hour. Thank you very much.
All right, well done. Thank you so much, Benjamin. I think we asked our questions during the presentation, which is a good way to do it. And I loved it's super creative. So he took an idea that was just a project for bread and turned it into a complete digital twin in the cloud, and has it was absolutely brilliant. So well done. Thank you, Benjamin. We hope to invite you back to our virtual lab this week, and you can take a look at some of our projects and help us try to figure out which way we need to go and inside of Edge Impulse to be able to do it the best. So thank you so much.
Thank you all.
Cheers.